Hello everybody, welcome to my video. This video is for the kidnapped vehicle project of the Udacity self-driving cars Nanodegree program. This project required us to localize a self-driving car through implementation of a particle filter, two-dimensional particle filter in C++. So localize means that we want to know the precise location of the car as it's driving. Um, Now we obviously can have the rough location of the car through our GPS if the GPS is working in that area within, let's say, about a 10-meter accuracy. But obviously 10-meter accuracy is not enough for a self-driving car to drive successfully on its own. So we need a higher accuracy, and that's why we need to localize the car so it knows its precise location within a very small, like a centimeter range accuracy, so that it can drive efficiently. So let's get started. This project is required us to implement a, like I said, two-dimensional particle filter. Now, particle filter, we'll get into the theory, the basics, as much as we can in context of the project. So first off, what I want to do is I am going to show you how the project would look like when it's done. So I'm going to run a visualizer small clip. This is from the course itself. This is not from my project. So it will show you how the project will look like when it's done. So I'm going to start the small clip now. So you see, this is the self-driving car here. The circle around the car is my best estimate of the particle, my best estimate particle. And the small boxes on the periphery as the car is driving are the landmarks. So those landmarks locations were given to us. I will talk about that in a second. And so as you see, now the blue lines are from the particle to the landmarks, and the green lines are from the car to the landmarks. And since these lines are pretty much overlapping, therefore this particle filter is working well. The car is localizing to a high degree of accuracy. You can see that from the error rate also, x, y, and yaw. XY coordinates, and yaw is the heading, the direction angle of the car. So that error is between the location of the car and our best particle. So having said that, next off I want to show here a flow diagram, so that so first of all, a particle filter is a realization of a Bayes filter. Bayes filter is an important concept. It involves a loop of prediction and measurement update. So it's motion model and observation model. It runs into loop to accurately estimate. And there are many applications of Bayes filter. Now this example we are seeing here is a particle filter, which is being used to localize the self-driving car. Another application is a Kalman filter. I have another video on that for my other project, which required to estimate the position of a bicycle around a self-driving car as the bicycle is moving. So in a summary, Bayes filter, like I said, involves prediction step here and update step in loop. And obviously we provide some initial values, and then it predicts based on what it knows. Then measurements come in, and then it updates its estimate based on the estimate based on those measurements, and then it goes back into the loop. It predicts again based on what it knows. then measurements come in, and so on and so forth. So that's in general is the flow of a base filter. So now let's look at the flow of this particle filter that we are going to implement. So first step, as you see here, this green box is, oh, let me minimize this a little bit. So this green box, initialization. So we initialize a certain number of particles, which are our estimates, for the where the self-driving car is. Now, again, particles are nothing but our estimates of the where the car is going to be. So we initialize them at different positions. Now, we initialize them based off of the initial estimate that we got from GPS. We couldn't possibly initialize them. I mean, if we didn't have a GPS estimate, we wouldn't know. Then our so-called state space would be the entire world, and we cannot have estimates feasibly have estimate of the car all over the world. It would probably not be a feasible approach. So we take the initial estimate from the GPS, and then we add sensor noise here, Gaussian noise here. We use the normal distribution function, and with our initial estimate as the mean and the sensor noise as the standard deviation, and we come with the estimates of the particles along that normal distribution. Now the next point here is how many particles to initialize. The concept here is that if we have too many particles, then the localization process will take longer time, and we want to localize the car in real time. So therefore, there has to be a balance between too many and too few particles. If we have too few particles, then what happens is that we may have a situation where we may not have a particle in the vicinity of where the car actually is. So we may not have a good estimate. So there has to be a balance. It was suggested maybe 100 particles may be good. So I used 100 particles for my project here. All right. So next, and we initialize the weights of all the particles to 1. Weights meaning probability. So because at this point we don't know which is the right estimate, so we just say the probability or the weight of each of those particles is 1. So let me show here the C++ code. So now this project required us to write the code for all these functions that we will see in this flow diagram here. Initialize, predict, update, step, resample. We haven't talked about anything other than initialization at this stage. So I just want to show, while we are at it, the initialization function. So we were required to write the code in this particle filter.cpp file. So initialization function will take x, y, the initial estimates which were provided by the simulator, and theta heading, and then the noise was given here in the main.cpp file. So main.cpp file is the noises are given here. So going back to the initialization function here, we see the number of particles is 100, like I was saying a second ago, and then the first element is x noise, and then y noise and theta noise, and then we're using these normal distribution function and this default random engine function to come up with those particles locations. Good. So this was the initialization step. Okay. Now next step is prediction step. So now we are going to predict where our particles are going to be at the next time step. So there are a bunch of, there is a set of mathematical equations. Um, so let's see here. I'm going to pull up a couple of images here. So let's see here. So the formula is xf, which is the new estimate of x coordinate for for a particle. Each particle is initial position plus velocity over yaw rate, which is change in heading, sine of yaw plus yaw rate times time steps minus sine of yaw. Similarly, for y coordinate, initial y plus velocity over yaw rate, and the new heading is old heading plus yaw rate times time steps. So this is when yaw rate is not equal to 0. There's another set of equations for when the yaw rate is 0. It's right here. New x is old x plus velocity times time steps time cos of yaw. Similarly for y, and new yaw or new heading is old heading because the yaw rate is 0. Good. So now let me go back to the flow diagram here one more time. So you see in the prediction step, we were given yaw rate and velocity. So yaw rate and velocity, this is called control data, and it's given by the simulator. We'll see the simulator. So main.cpp is actually interacting with the simulator, calling the simulator, and the simulator provided this control data, this initial estimate data. So like I said, v control and yaw, the heading that constituted the control data, and that was used in the prediction step equations, and sensor noise was added. So now I want to show the prediction step in the equation here. So we pass delta t, noise, velocity, yaw rate, and we use these equations here that I just showed. So if yaw rate is 0, then this equation we just saw, and if yaw rate is non-zero, then these set of equations. Okay, perfect. And this is how we incorporated the noise using a normal distribution. Okay, perfect. So now this was the prediction step. Okay, so now the next step is update step or update weights. And this is a bit of a tricky step because it involves a couple of steps on its own. So first of all, we are passing the map landmark positions. Landmarks were the small circles that we saw on the periphery or along the path of the self-driving car, and the sensor measurements through the simulator to update steps. So it's typical Bayesian prediction update, and in update is happening based on the new measurements that are coming in at each time step. So now update step, the first step in update step actually is something known as data association. And to explain data association, let me show you this image, and we'll take an example and see how data association works, because then update step, update weights works off of that. So this in red is our self-driving car. This P box is one of the particles, because we are going to do it for each particle. And in the sensor range, 3 observations were made. And sensor range is something which is defined in one of the files here. I want to say main.cpp right here. Sensor range and time dt is defined uh, in the main.cpp, and main.cpp is also creating an instance of the particle filter class. Particle filter class is defined in particle filter.h, and the functions initialization, predict, update, resampling are specified in the particle filter.h, and then they're defined in the particle filter.cpp file, which we had to write the code for. Okay, going back here. So there were three observations made in the sensor range. Observation 1, 2, 3. Now these observation 1 in vehicle coordinates, we have to see these observations with respect to the car. So car is at 2, 5. So observation 1 with respect to the car is 2, 2. It's 4, 7 minus 2, 5. Similarly, observation 2, which is at 5, 3 in this Cartesian coordinate, but with respect to car, it is 3 minus 2, and observation 3 is 0 minus 4. Now, we need to transform these vehicle coordinates. Now, vehicle coordinates, you see the car, wherever the direction that car is going in is x right here, and the left to that is y. So this is the vehicle going in this direction right here. So that's x, and to the left is y. Okay, cool. So now we need to, like I was saying, transform these vehicle coordinates to the map coordinates. So how do we do that? Again, there is a set of equations. So let me pull up two of these pictures here. So for each particle, sorry, that's not the one. For each particle, we go through this equation. So theta is the heading. So we saw for our blue particle so let's say we are doing this for, we are transforming observation 1, 2, 2, and for this particle 4, 5. Okay, so xpyp is 4, 5, theta is minus 90, xcyc is 2, 2, and then we have to come up with xm using this matrix here. So we do that for each of the observation to come up with corresponding transformed observation. TOBS 1, let's call them TOBS 1, TOBS 2, and TOBS 3 for T for transformation. So TOBS 1, using that formula, came out to, let's see, 6, 3 right here. 6, 3 right here. TOBS 2 came out to 2, 2. This is 2, 1, so 2, 2. And TOBS 3 came out to 0, 5. So now we have to associate each of these transformed observation to the nearest landmarks. So TOBS 1 being 6, 3 was associated with L1. TOBS 2 was associated with L2, and TOBS 3 was equidistant from L2 and L5. And L's are landmarks. Landmarks are like buildings, for example. So to summarize this step here, we got the observations in the vehicle coordinates. We transformed each of these observations into transformed observations using this matrix. This matrix, by the way, is called homogeneous transformation matrix, and it worked out to this formula actually. So we did that for each transformed observation. We associated them with a landmark. So TOBS 1 was associated with L1, TOBS 2 with L2, and TOBS 3 either L2 or L5. Cool. So now we have this. Now we need to update the probability. So for each of those, we use this formula here to get the weight or probability. So probability of, so we do this for each set of transformed observation and the associated landmark. So TOBS 1 was 6.3 and it was associated with landmark, let's say 5.3, 6.3 and 5.3. So in this equation, 1 by 2 pi sigma x sigma y, sigma is noise, x will be 6 and y will be 3. So TOBS 1, for TOBS 1 coordinate will be x, y, and mu x, mu y will be landmark L1 coordinate. So that's how we get the probability of this. And then we do this for TOBS 1 and the associated landmark, TOBS 2 associated landmark, TOBS 3 associated landmark. We multiply all these probabilities to come up with the weight of that particle. And we need to normalize it, the weight between, so that the values are between 0 and 1. Because these weights are now used in the next step, which is resampling, which we will get to in a minute. So I hope that was clear. Update step, like I said, it involves first data association, converting the vehicle coordinates to map coordinates, call them transform observations, associating them with the nearest landmarks, then coming up with using the Gaussian multivariate probability distribution, 1 by 2 pi sigma x sigma y e to the power minus x minus mu x square and so on, to come with the probability, calculate that for each TOBS and landmark associated, multiply that to come up with the probability / weight for each particle. Cool. All right, so that was that. So let me show that in the C++ here. So first was data association. You see it's calculating the nearest distance here and then associating to a landmark ID. And then update weights will be using that 1 by 2 pi sigma x sigma y, this function here, e to the power of minus x minus mu x, that function that we just talked about or showed. Perfect. So we have talked about all this. Now next step is resampling. Okay. So what's resampling? Now resampling is, resampling is a process where we pick up the weights, pick up the particles based on their weights for the next time step, next iteration, because this goes in a loop, right? Prediction, update, resampling, then again prediction, update. Initialization was done just at the get-go. So what's resampling? So resampling is a process. We pick the same number of particles, but we pick them in a way that the particles with the higher weight, they have a proportionate probability of being picked up. So each particle has a proportionate probability of being picked up in proportion to their weights, and then the lower weight probabilities are more likely to be discarded, and the higher weight particles are more likely to be made, they make copies of those and more likely to be picked up. So now resampling in C++ is done through, there are couple of functions, discrete distribution or uniform real distribution, and you just pass these arguments and it does it on its own. Perfect. So I think that actually summarizes the flow of the particle filter approach to come up with the localization of the car. Now what I hope to do here is I want to run my project work here and then show you. So this needed a GPU. Okay, and let's see here. So I think I go here and I run this command clean.sh to clean up, then build. The modified files were already uploaded in this file here. And I forgot to show you the map data.txt, which is nothing but um, XY coordinates of each of the landmarks. But the simulator was providing that if I ran the project on my own machine, then I needed to but download this file and call it, but the simulator was doing it. Okay, now I'm going to run .sh, which will launch the simulator. Okay, simulator here, 64480 fastest. Okay, so it's this project here. I'm going to select that and going to start it. And you see now one difference here in my run or is that the blue lines which were supposed to be from the particle to the landmarks, that is somehow disabled in the simulator. I could not figure out a way to enable those, but otherwise you see the error is low. You see the particle surrounding the car and you see it's moving along the landmarks. So the green lines are the laser lines, are the lines from the car to the landmarks, but the blue lines are not there. The error rate is low, and in the end, it should say passed, I think. So that sums it up for particle filter. If feel free to leave comments, and like I said, I have another video out there. Which is for Kalman filter, extended Kalman filter, which was another project in the program. And hopefully this video was helpful. I also have write-ups for my project on Medium, and those could be seen here, medium.com at manish.johari, Jauhari. Thank you for watching, and that's all. Bye.